Hi, and welcome to this video about electric forces and electric fields. My name is Callie Chappelle, and this video is made for Physics 235 at the University of Michigan, which is Physics 2 for the Introductory Physics sequence for the Life Sciences. So, the electric force and the electric field happened right at the beginning of the semester, and are, in my opinion, the most complicated topics of the entire semester. And I think a little bit of it is a lot of this material is new, and it's really, really abstract. So I'm going to try to break it down in an easy to understand format, so you get an intuitive understanding of what we're talking about, so it's easier to apply these to more difficult questions, not just plugging and chugging. So, before we begin, there are four fundamental forces. There's gravity, which we studied in mechanics, so that was Physics 1. There's the electromagnetic force, which is actually, we're going to break down this class into studying electricity and magnetism separately at first, and then we'll combine them at the end to find out that they're actually the same force at the speed of light. There's a weak nuclear force, which is radioactivity, which we'll look at in brief at the very end of the course. And finally, the strong nuclear force, which is what binds quarks into protons and neutrons. This will be briefly hit upon, I believe, in the magnetism section, but don't quote me on that. So, what exactly is a force to begin with? Well, we'll know from Physics 1 that a force is just an interaction that tends to change the motion of an object. So, a really good example of a force that we talked about in Physics 1 was the gravitational force. So let's take a look really quick at just what we know about the gravitational force. So, let me see if I can grab there we go. We know the gravitational force is something that we just intuitively know. If we take a rock and drop it down, the gravitational force will cause the rock to fall to the ground. And we're going to look at a similar force, which is the electric force. Okay, so the electric force is the force that is exerted between two charged particles. So you may have noticed when you were a kid that if you took a balloon and you rubbed it up against a piece of fabric, it would stick to your hair. And that was because you changed the charges on the balloon. You made the balloon either negatively or positively charged relative to your hair, and it made an attractive force. So that force is the electric force. Okay? And the electric force is described as a vector. I know you're probably groaning to yourself that it has to deal with vectors. So when we're dealing with vectors, it depends on the sign or the direction of the vector as well as the magnitude. Okay, so we're dealing with vectors. So we know that the electric force then has to depend on the sign and the magnitude of charges. So where the gravitational force depended on the mass of the two bodies, in this case, we're looking at the sign and magnitude of charges. So what are charges? Well, these are just plus. We're going to think about these as just plus and negative. So things that are positively charged, things that are negatively charged. So in nature, this is usually electrons, and then positive is usually the lack of electrons. So we can describe the electric force. So let me write electric force here. Electric force using an equation called Coulomb's law. So let me write out the law first, and then we're going to define what everything means. So the force electric, which again, remember, is a vector, is equal to K Q1 Q2 over R squared in the direction of R hat. Okay, so this part of the equation is going to give us the magnitude of the electric force. Magnitude, oh god, I'm so bad at spelling. Magnitude, this is a T, and this is going to give us the direction. Okay, so let's define what all of these things mean, and as well as their units. So I'm going to do that in this slightly lighter yellow. So this, as I said, stands for the electric force. And that is simply the force that's exerted between two charges, or two or more charges, okay? And this is going to be a vector, which is why I have a vector arrow above it, okay? So here is K, and that's just a constant, and that constant, and electric force is in, like all forces, are in newtons. This K is 9 times 10 to the 9th, and that is in Newton meters squared over Coulomb squared. And I think you'll see where this comes in a little bit. Okay, why this is the units. Okay, so here we have Q1 and Q2. These two are just the charges in question. Okay, and then here this R squared Okay, and this is going to be in a new unit called coulombs. Okay, and that's just a unit that we use to describe the amount of charge in a particular charge. And this r squared is the distance between Q1 and Q2. So let's draw a picture of what this means and look at it one more time. So let's say that I have a positive charge here and I have a negative charge here, okay? And let's say that each charge has a charge Q, and we're going to call this 1. I'm just going to call this 2. And charge 1 has a charge of 1 coulomb, and charge 2 has a charge of negative 1 coulomb, okay? So let's figure out what the force between it is. Well, first, let's figure out the direction first. And you probably have heard before that opposite charges attract and like charges repel. So the direction of the force in this case, if we're asking about the force of, here's a new convention, of 1 on 2, so here is the one acting. First you list the one acting, and then you list the one acted upon. If we want to know just the direction of force, the force of 1 on 2, because it's attractive, this force would be to the right. Okay? That's because it's attractive. So we know like charges repel, opposite charges, that just means charges attract. Okay, and this makes intuitive sense. You can think about, even though we're not talking about magnetism, think about a magnet. Two opposite sides of the magnet attract. Two of the same side, north-north, repels, whereas north-south attracts. Okay, and then we can figure out the magnitude. So let's just say that this is separated by 1 meter. Let's just make the numbers really easy. The magnitude can be found using Coulomb's law. The force of 1, 2 equals K, which is, remember, 9 times 10 to the 9th Newton meters squared over Coulomb squared, times Q1, which in this case is 1 coulomb, times negative 1 coulomb, all over R squared, which is 1 squared. Okay, so this just comes out to be negative 9 times 10 to the 9th. Okay, so that would be the magnitude, and because we're taking the magnitude, this is going to be positive or negative in the direction that's stated here to the right. Okay, so that is Coulomb's law. So what happens if you have multiple charges? Well, if you want to figure out the force on one charge due to multiple charges, you have to use what's called the superposition effect. So let me allow you to visualize what I'm talking about. So let's say that we have a positive charge here, and we have a negative charge here, okay? And we want to know what is force on negative charge. Okay, so let's just call this charge A, this charge B, and this charge C. So we know that, well, first let's just think about what we know. Well, we know that we have opposite charges here, so they're going to be attractive, okay? So we're going to have a force that goes like this from B onto C, an attractive force, and an attractive force also from A onto C. Okay? And then how do we figure that out? Well, how do we figure out the magnitudes of those forces? Well, we use Coulomb's law, which is right here. But what do? Well, it makes intuitive sense that the total force on C just equals the force of A on C plus the force of B on C. So we're going to add this. Right, so this is the force of A on C, and then we're going to add this, the force of B on C, okay? And remember, we are talking about vector quantities here, so that's going to create a new vector, this vector total of C. So what do we do when we add vectors? Well, remember, we actually have to remember how to add vectors. So we're going to use the tip to tail method. So let's say that this is force of A on C is this lighter blue color. So I'm going to draw this down here. We're going to add that vector to this vector, which I'm going to redraw here in this slightly green color. That's the force of B on C. So I'm going to add tip to tail. So our resultant vector force, the total force on C is this vector, okay? So this is sum of all forces on C. Let me just relabel these so they're a little bit easier. This is the force of A on C, and this is the force of B on C. So we're going to have to remember how to add vectors, so this is just a really quick overview. But this makes intuitive sense, right? If you have multiple forces acting on one thing, how do you figure out the total of the total force on C? Well, you just add up the forces that are contributed by these two other point charges. Okay, so let's do the very last thing on this topic, and this is looking at electric fields, okay? Electric fields. And in my opinion, electric fields are the most confusing topic that we talk about. Okay, so what is an electric field? Well, that is just the electric force per unit charge. Well, that doesn't really make a lot of sense. Well, let's think about what an electric field looks like. So let's say that I have a positive point charge. What the electric field looks like at this positive point charge is just these vector arrows, which represent the electric force going out in all areas. So in order to have a force, as we know, you need to have two different bodies, right? To have a gravitational force, for example, on planet Earth, you need to have a, something that's dropping and something that it's coming towards. Okay, you need to have two bodies. But in order to have a gravitational field, so like if this is the Earth, you don't need to necessarily have something around it for a gravitational field to be like propagating in space. And the same thing is true for the electric field. So the electric field are all of these field lines that are propagating all around. And so how do you know what the field lines are if you don't have another charge? Isn't that how we define the electric force? Well, that just has to do with the special way in which we're defining the electric field. So we define this as the force electric per unit charge. So what we like to do to figure out what this electric field is, kind of elusive electric field, is to think about what happens if we put a point charge in the electric field. What would be the resultant direction of the force? So what is a point charge? A point charge is just an imaginary tiny positive charge, okay? So that is point charge P. So if I put point charge P here, we would see a repulsive force, okay? So we would see a force that's going in this direction, okay? It's going to be moving, making these two things repel, making this repel away from this, so to have a resultant electric force going away. If I put a point P here, again, we would have an electric force that's pointing away, okay? So we're having force electric pointing away. So imagine if we had an infinite number of P's all around, all the tiny force vectors added together would together comprise the electric field for this particular charge. So again, like electric forces, we have an equation that quantifies the electric field. So like we said, as we defined the electric force as the vector force electric, we define the electric field this way, using this equation, okay? So E stands for electric field, okay? And that equals the force on a test charge, okay? So that is this P, okay, times the charge of the test charge, okay? And that equals K times Q test charge over R squared in the direction of R hat. So this is what makes it a vector, okay? So how do we actually do this using calculus? So I gave you kind of an intuitive understanding. In actuality, what we are going to do is we actually express the field in terms of its derivative, dE, for each piece of charge, and then we find the vector sum of each dE to get the total dE for the charge. But you don't need to worry about this. This is not a calculus-based physics class, so we are not going to get into it. So these lines that show the electric force all around a particular point charge are called electric field lines. Electric field lines. Okay, and in order to draw these electric field lines, which you're going to have to get pretty good at understanding, there are a couple of rules. So here are the rules. And I want to lay this out to you really early because you need to get good at kind of gaining intuition about these rules in order to fully understand the types of diagrams that you'll be asked to interpret, okay? So the first thing is each charge is a source, and these are positive charges, or a sink. You will not see electric field lines emanating from something that is not charged, okay? And like we said, the direction of electric field lines go from source to sink, okay? Sink, okay? And this represents the electric field line, or lines in this case. Okay, the second one is the number of lines attached to charge is proportional to the magnitude. So the electric field, so let's say we have 2 point charges. We have point charge A, and we have point charge, point charge B. If A has lots of lines emanating from it, say it looks something like that, and B has fewer electric field lines emanating from it, we can say from this diagram that the electric field of A is stronger than the electric, let's do this in the right color, the electric field of B. Right, so the next rule is that every line starts at a positive charge or infinity, and every line ends at a negative charge or infinity. So what does this mean? This means that, okay, so every line, let's just write this down, starts at positive charge or infinity, or positive infinity, starts at negative charge or negative infinity. Okay, so again, what does this look like? If we have a positive charge, the field lines will emanate radially from it in all directions. So in this case, these lines are starting at positive and going to negative infinity, going to infinity. And if you have a negative charge, field lines will come to it, okay? They'll come to it. If you have multiple charges, so let's say you have what's called a dipole, so that's just 2 charges, field lines will go from the positive charge to the negative charge, like this. And you can find some really cool images of this online, and hopefully I'll make a slightly more advanced video about how this actually works in a little bit. But you'll see something like this, okay? So you'll see the lines starting at positive charges and ending at negative charges. The fourth rule is that the strength of the electric field, this represents the electric field, the strength of the electric field, which actually in this case is a magnitude, is determined by how close the lines are, equals how close lines are. So if I wanted to draw the strength of an electric field, I would draw close to the point charge, the lines really close together. And as you get farther away from the charge, the electric fields move farther apart, and that's because further away from the source, the electric field degrades. Now, how do we know that? Well, remember that the electric field is defined as kq over r squared. So if r increases, then E decreases at a rate of 1 over r squared. So that's why this is the case mathematically. And finally, the direction of the electric field is tangent to the line, okay? So that means that we can have an electric field, that the electric field can have field lines without another charge. So what does this mean? This means that if E equals F over Q and F equals ma, then that means that acceleration is also tangent to the line. Actually, let me just write this down, number 5, so we have it on paper. Direction of E is tangent to the line. Alright, so I just wanted to go over these really basics of the electric force and the electric field. I'm going to do a couple of other advanced videos talking about specific cases of the electric force and the electric field that you'll need to know, as well as electric potential and electric potential energy. So hope to see you in those future videos, and good luck in physics.